Now we're going to look at some shortest path algorithms. And to get used to some of those ideas, I would strongly encourage you to look at the in-class activities called Introduction to Shortest Path Algorithms. Okay, so we're going to look at two particular algorithms that help us find shortest paths between a given vertex and all the other vertices in a weighted graph. So first, we're going to review weighted graphs again. We're going to define what it means to be the shortest path between two vertices. We're going to learn about Dijkstra's algorithm. That is one way of finding the shortest path between vertices. And then we're going to do a variation on Dijkstra's algorithm that's going to be a little bit better. It's called improved Dijkstra's algorithm. All right, so here's what a weighted graph is. Just in case you don't remember, a weighted graph is a graph in which each edge is labeled with a real number. So here's an example of a weighted graph. Notice that all the lines between the vertices have numbers near them that are associated with those edges. So one way we can think of the weights of these edges is we can think of them as distances between the vertices. And if we do that, then the shortest path between two vertices is a path whose total weight is as short as possible. So the official definition is if G is a weighted graph and if V and W are vertices in G, then the shortest path between V and W is a path in which the sum of the weights of the edges of that path is as small as possible, is a minimum. So here's our weighted graph again. And if we want to find the shortest path between A and B, that would actually be the path ACB. Looking right there, A to C has a weight of 2, C to B has a weight of 1, so the total weight is 3. And notice something interesting about that. It is actually shorter to go to from A to B through C than it is to go directly from A to B from the edge between those two. Because that edge has a weight of 4, which is more than the 3 that you get from going from A to C and then to B. So we got to be careful about things like that when we're finding shortest paths. All right, so our first algorithm to find shortest paths between a vertex and all the other vertices is called Dijkstra's algorithm. So what it does is you start with a vertex V and then find the weight of the shortest paths between V and every other vertex. So the algorithm starts with just your vertex V, and you label it with a distance of 0 because you know exactly how long what the distance is from V to V. The distance is 0. So then what happens is at each step you find the distance between V and the closest vertex whose distance from V has not been determined. Right, so what happens is that at any given point in the algorithm is you have maybe some vertices that you know how far they are from V. And then what you want to do is add one vertex to that list. So what you're going to do is look at all the vertices that are adjacent, not to V, right, but adjacent to vertices whose distance from V you have determined. Right, so we know how far from V these other vertices are, and then what you do is you extend to another vertex that you don't know that is adjacent to one of those vertices. And what you do is you use the distance from V to the known vertices to help compute the distance from V to the new vertex that you don't know. And then what you do is you also keep track of important vertex information to be able to figure out the shortest path to V from that information. And then you keep repeating this algorithm recursively until all distances to V are known. And what's going to happen is it's going to feel a little bit like Prim's algorithm for finding minimum spanning trees, where you're starting with V and you're sort of extending to new vertices from vertices that you already know. All right, so here is our weighted graph, and we're going to find the distance from A to all the other vertices. So we're going to actually just start with A. I'm going to put a little rectangle around that one, and we know how far A is from A. It has distance 0, and I put a little dash there because that just tells me that we don't need to know any additional vertex information. We know exactly how to get from A to A. Duh, you just do nothing. So for the other ones that where I put that dash here, the other ones I'm going to put vertices to tell you where you came from. And I'll show you when we get there. All right, so the only known vertex we have right now is just A. And so we're going to look at the other vertices that are adjacent to A. That's going to be B and C. And the closest one of those is going to be C, which has distance 2. So I'm going to put down a 2 for its distance, but I'm also going to put down A that tells me the way I get from A to C is to go directly from A to C. So now what we're going to do is we're going to look at A and C. Those are the two known vertices, and we're going to look at the vertices adjacent to those. So A is adjacent to B, C is adjacent to B, D, and E. And then we're going to look at all those distances. So I'm going to start with C. C is adjacent to E. It has a distance of 10 from C to E. But also remember, we have a distance from 2 from A to C. So if we go through that edge, we're going to have a total distance of 12 from A to C to E. If you look at D going through C, that has a distance of 8, but then again we add the distance 2 from A to C to give a distance of 10. From C to B, we have a distance of 1, but we add the 2 to get a distance of 3. And then if we look at A, that is adjacent to B, we have a distance of 4. So we look at all those distances, the 4, the 3, the 10, and the 12. We take the smallest of those distances, and that's going to be the distance that we do. So that's going to be from B, and that distance is going to be 3. And then I put a C there to say that, hey, the way we got to B is from C. That was the distance, that was the vertex right before we got to B. Just so that nobody gets confused and tries to get there directly from A. All right, and now we keep doing the same thing. We look at all the adjacent vertices from A, B, and C. That's just going to be for D and E. If we go from C to E, that's 12 again. If we go from C to D, that is 10 again. If we go from B to D, that is going to be 3 plus 5 is 8. The smallest of those is going to be a distance of 8, and that is gotten from the vertex B. So we want to go from B to D to get that distance of 8. So now that we have 5 known vertices, we look at all the vertices that are adjacent to them. That's going to be E and F. Now we can get from we can go from D to F, that'll have a distance of 14. We can go from D to E, that has a distance of 10. We can go from C to E, that gets us a distance of 12. The smallest of those distances is going to be 10 going from D. And so now we know about E. And then we have one more to do. We have F. If we get there from E, we have 10 plus 5 is 15. If we get there from D, we have 8 plus 6 is 14. 14 is the smallest of those distances. We get a distance of 14, and we know we get there from D. So next we're going to do improved Dijkstra's algorithm. Improved Dijkstra's algorithm works almost exactly the same as Dijkstra's algorithm. First of all, it answers the same question. We start with a vertex V, and we find the distance from that vertex to every other vertex. But the big difference between Dijkstra's algorithm is instead of having to figure out one vertex at a time, we're gonna find a bunch of weights at once, but a lot of them are going to be temporary. And what happens? We have these temporarily weighted vertices that we have some idea that might be the true distance from V to that given vertex, but we want to make sure before we make those permanent. So the temporary ones will change later when we're sure about the distance. And some weights are going to be permanent. Those are the ones we are 100% sure that is the distance from V. So what we're going to do is, again, we're going to start with V, and we're going to label that with a distance of 0. That one's permanent because we know exactly that one's 0. Then we're going to, at any given step in our algorithm, there are some we're going to be positive of, that those are going to be our permanent labels. There are some we're going to be kind of sure of, those are going to be our temporary labels. And what we're going to do is we're going to look at the vertices adjacent to the permanent labels, the ones we're absolutely sure about. We're going to use those permanent vertices to figure out which ones are adjacent to those to estimate the distances of the new vertices. Those are going to be temporary. And then out of all the temporary distances, we're going to look at the shortest one. We're going to make that one permanent. And then we're going to repeat the algorithm recursively until we know all the distances. So you can see that this algorithm is a little bit looser because we're making some guesses, some sort of wild guesses out there that we eventually make more precise. All right, so once again, we're going to start with A that has we're going to look at the distance from A to everything else. The distance from A to A is 0. We don't have to do anything there. Now what we're going to do is we're going to look at all the vertices adjacent to A. That's going to be B and C. And then those are going to get temporary labels of 4 and 2 because that's what we get when we travel along those edges. The smallest one of those distances is C, that is 2, so that is going to be permanent. All right, so now we're going to look at A and C. We're going to look at all the vertices that are adjacent to one of those. So we still have B. C is adjacent to D and E, and so we're going to look at all those distances. Well, we look at the temporary labels. We notice that from C to B, we have 2 plus 1 is 3, so that makes that label a little bit better. From C to D, we get 10. From C to E, we get 12, and now we have 3 labels, 3, 10, and 12. We take the smallest one, which is to B, and we make that one permanent. That one has a distance of 3. All right, so now we have 3 permanent labels. Now we look at all the vertices that are adjacent to those permanent labels. Again, that's just going to be D and E. We look at all the possible distances that we can get from those. So if we're looking at D, D can come from B. That gives us a distance of 3 plus 5 is 8. That is smaller than the distance of 10 that we had before. E has the exact same distance before. It has 12. Now we have 2 temporary labels, 8 and 12. The smallest one of those is 8. We make that one permanent, right? We make that one permanent by putting a rectangle around it. And now that gives us a 4th vertex that we're positive about. Now our permanent vertices are A, B, C, and D. We have one more permanent vertex that we get from D that has a temporary label of 14. Notice now the E, it used to be 12 coming from C, but we can also get there from D, which is also permanent. A plus 2 is 10. That gives us a better label of 10 instead of 12. Now our temporary labels are 10 and 14. The smallest of those is 10. We can make that one permanent. And now we just have to figure out F. We can get to F from either D or E. That's our 2 permanent labels. If we get there from D, we get 14. If we get there from E, we get 10 plus 5 is 15. 14 is smaller, and so that is our permanent label. So now I think you're ready to work on the Dijkstra's algorithm file that's on the PDF included with this video.